In this video I talk about symbolic integration and I present some higher functions that are defined in terms of definite integrals. Please open the script example symbolic integration. It can be found in the folder examples 6 in TIS, and let's put a breakpoint in line 2 and run the script. In the first section, I consider a simple example, a harmonic oscillation. We start by defining a symbolic variable x and 4 symbolic parameters a, b, c, d. The symbolic function f depends on the variable x and 2 parameters a and b, and it has the form sine of a times x times exp of minus b times x. We see now in the workspace on the right hand side that f is a symbolic functions. We can now compute the indefinite integral or the antiderivative of this function by invoking the Matlab function int. Int has 2 arguments. The first one is the symbolic function to be integrated, and the second one is the integration variable, in this case x. You can see the form of x of capital F in the command window. Now let's choose 2 numerical values for a and b. Let's say we choose a naught equals 1 and b naught equals 2. And we can now define another symbolic function which depends only on x. I call it f naught, because a and b are now substituted by a naught equals 1 and b naught equals 2. So f naught is now a function handle which depends only on x. Now we can integrate this function again, and we get the antiderivative capital F naught, which is the function shown in the command window. And we can also obtain this function by substituting a naught and b naught for a and b in the indefinite integral f. So these two have to give the same result, and of course they do. How do we compute definite integrals, or areas if you want? Now this is also done by the function int. We just add 2 more arguments which specify the limits of integration. These are the symbolic variables c and d. And this is now the definite integral of the function small f for the integration limits c and d. Now we can also specify c and d to 2 numerical values. Let's say c naught equals 0 and d naught equals 5. And we can now substitute our numerical values into the definite integral, capital I. We get a symbolic constant, which we now can convert to a numerical constant by the function double. It's about 0.2. Of course, we get the same result if we integrate the function small f naught in the limits from c naught to d naught. Remember that f naught was the special case of f for a equals a naught and b equals b naught. In the second section I show some examples of rational functions. You know probably that antiderivatives or indefinite integrals of rational functions can always be expressed in terms of elementary functions. So my first example is a general rational function a times x plus b over c times x plus d, where a, b, c, d are arbitrary symbolic constants. So this is the definition of the function small f, and its indefinite integral capital F also depends on x and those for constants, and it has the form as you see in the command window. Now we can try to differentiate capital F again and compare it to the function small f. So this is a differentiation of capital F with respect to x. I can invoke the function simplify to get the simplest algebraic form of this derivative. And here you see immediately that it's indeed identical to small f. Let's now try a slightly more complicated rational function, the ratio of two polynomials of degree 3 in the numerator and of degree 2 in the denominator. This function is called small g, and its indefinite integral is called capital G. And you can see that it's can be expressed in terms of logarithms and other algebraic operations. Let's differentiate it again. So dg is now the first derivative of capital G. In order to compare it to small g, we have to simplify it, and you see that it's, of course, identical to small g. Another example, again, a ratio of two, a quotient of two polynomials, small h. The antiderivative capital H is again written down in terms of logarithms. You see it in the command window. If we differentiate with respect to x and simplify, we recover the original definition in small h. Next, I consider functions of the form power of x times exp of x, sine of x, cosine of x, or log x. Let's start with cases where n is an integer, a natural number. In this case, there is always an antiderivative which is expressed as a polynomial times the exponential of x. For instance, if we define small f as x to the third times exp of x, then the antiderivative, capital F, has this form in the command window. It's exp of x times a polynomial in x. The same is true if we replace the exponential function by the sine function. We again have an antiderivative which can be expressed in terms of sine x, cosine x, and polynomials in x. The same is true for the cosine. So the antiderivative of x to the third times cosine x is again the function capital F shown in the command window, expressible in terms of sine x, cos x, and polynomials in X. Let's try the similar approach for a power of X times log X, where the power is an integer, power, a natural number. So we look at the example x to the power of 3 times log X. If we look for the antiderivative, we get the function capital F shown in the command window. It's expressible in powers of X and log X. Now, what about choosing an arbitrary power exponent? So let's now define a symbolic variable n, which we take to be the exponent of X. Let's start with the function x to the power of n times log X. So this is now the function small f, and we look for the antiderivative, the indefinite integral. And here we see that there are two cases. In the case n equals -1, we get the function log x squared over 2. In all other cases, we get the function shown in the command window in the bottom line on the right hand side. So it's x to the power of n plus 1 times an expression which contains log x. So in this case, we obtain a very general form of the antiderivative. Note there is now no restriction on n. This is true for arbitrary n, but we have to differentiate two cases, n equals -1 and n different from -1. Now let's try the same approach for x to the power of n times exp of x. N, again, a symbolic variable with no restrictions. So what do we get if we compute the antiderivative for this function, small f, x to the power of n times exponential of x? Well, in this case, we don't get an integral in terms of elementary functions. Here we need the higher function I gamma, which will be explained in the next section. Let us now assume that x, a, and b are positive symbolic variables, so they take only positive values on the real line. And let's define the function small f in this way. So f is x to the power of a minus 1 times the exponential of minus x. The definite integral of this function from 0 to infinity is the definition of Euler's gamma function. It depends on a and can be computed by gamma of a. For instance, I can compute gamma of 3. This is 2. Gamma of 5 is 24. Actually, if the argument is a natural number, the value of the gamma function is n minus 1 factorial. A very important special value of the gamma function is gamma of 0.5, and that's the square root of pi. So let's continue in this section in the script. if the integration runs from 0 to, not to infinity, but to a value b, we get the so-called incomplete gamma function. And this is gamma of a minus I gamma of a and b. So I gamma is actually the integral of the function small f from b to infinity. We can evaluate this value by the function double. It's very close to 2. There is another way of computing this value by using the function gamma inc times gamma 3. So let's have a look in the help section. Let's look up I gamma and gamma inc. So I gamma is the upper incomplete gamma function. It's the integral from the second argument to infinity over this function where eta is the first argument of I gamma. This is a corresponding lower incomplete gamma function, but the function I gamma, which we are using here, is the upper incomplete gamma function. There is now a related function which is called gamma inc, which is another version of the incomplete gamma function. So this function is defined as the lower incomplete gamma function for parameter a divided by gamma of a. So this value is always between 0 and 1. So if you want to compute the lower incomplete gamma function, we can multiply the function gamma inc by gamma of a, and this is what we are doing here. So this is the incomplete gamma function for a equals 3 and b equals 10 times gamma of 3. This gives the same value as this integral over small f from 0 to b using the value 3 for the parameter a and the value 10 for the upper limit b. Okay, the gamma function, Euler's gamma function, is a function that rises very quickly with its argument. So let's have a look at gamma of 100. This should be identical to the factorial of 99. Let's have a look. Yeah, that's the same. You see they are slightly different because they are not computed the same way. This is just a product of all natural numbers from 1 to 99, and this is the value of the gamma function at x equals 100, which is computed quite a different way. It's sometimes useful to operate not with the gamma function itself, but with this logarithm, which is called gamma ln. So this is about 360. If we now take the exponent, the exponential of gamma ln of 100, we should retrieve gamma of 100. There is another function which is closely related to the gamma function, a so-called digamma function, which is the derivative of gamma over gamma. This is called psi in Matlab. The psi function has a very special value for x equals 1, you recognize this probably as the negative of the Euler-Mascheroni constant, which is very important in analysis. So psi is just the negative of Euler gamma, which is the function that returns the Euler-Mascheroni constant. Euler's beta function is also defined in terms of a definite integral. It depends on two positive parameters a and b, and in this case x is confined to the interval from 0 to 1, so it's certainly positive. We define the function small g in the following way. It's x to the power a minus 1 times 1 minus x to the power of b minus 1. And I recall that a and b have to be positive, larger than 0. The integral of this function from 0 to 1 is called Euler's beta function, and it's implemented in Matlab by the function beta, which depends on the two parameters a and b. There is also an incomplete beta function analogous to the incomplete gamma function. So the integral of the function g for the values a equals 3 and b equals 4 from 0 to 0.5 is the incomplete beta function. If you want to obtain its value from the function beta inc, we have to multiply this by beta 3 and 4. Because beta inc is again the lower integral divided by the value of the beta function. We can have a brief look in the help section. So beta inc, the incomplete beta function, we can see the definition here. So it's the integral of this function where z equals our a, w equals our b. This is the integral of this function from 0 to x divided by the value of the beta function for z and w. So if you want just the integral, we have to multiply the incomplete beta function beta inc by the value of the beta function, which is just what we do here. By the way, if a and b are natural numbers, then the function small g is of course a polynomial, and in this case we get an explicit antiderivative, which is also a polynomial. So another example, we now choose not integer parameters a and b. In this case, there is no explicit form of the antiderivative, but this is still an incomplete beta function. So we can express this in terms of the functions beta inc and beta. You see that the integral, have a look at the command window, the integral cannot be written down explicitly in terms of elementary or other higher functions, but we can use the higher functions beta inc and beta to compute this integral, which has this value. Our next higher function that we consider is the error function. The error function arises if we integrate functions of the type shown here in line 76. So in the simplest case, we just integrate the exponential of minus x squared. The integral of this function over the entire real line is square root of pi. If we now take the antiderivative, so the indefinite integral, we get a function which uses a so-called error function called ERF in Matlab. What's the definition of ERF? Let's have a look in the help section. So ERF, the error function, that's the definition. It's an integral from 0 to x over e to the power of minus t squared and then multiplied by 2 over square root of pi. So if we compute the integral over h from minus 5 to 5, for instance, this should just be the error function at x equals 5 times the square root of pi. We can also replace the minus x squared by plus x squared, and we get a related function which is called ERFI of x. The imaginary array function. The definition is given by this integral. So it's very similar to the error function, but we obtain it by replacing t pi by it, where I is the imaginary constants, and is closely related to the error function via the relation on the left-hand side of the integral.